Hello everybody. In this module, we will be discussing a specialized MAC algorithm which is adapted to wireless environments. MAC is a protocol of data link layer and it is used to regulate the access of medium when multiple users are using the medium. Now it is a requirement for every medium, but in wireless scenario, the wireless medium where the medium is air or atmosphere and the multiple users try to access the medium, collisions may occur. Therefore, specialized algorithms are required for wireless scenario. Now, the existing protocols for the wired network like CSMA-CD used for MAC cannot be directly used in wireless scenario for the reasons which occur or the problems which occur typically in the wireless scenario, and these problems are known as hidden and exposed terminal problem and near and far terminal problem. So therefore for a wireless environment, specialized MAC algorithms have been devised. Now MAC algorithm should have a goal of the collisions should be less, the throughput should be more, channel utilization should be maximum, there should be fairness among the users, and there should be no jitter or delay. So in this module, we will discuss that what is the motivation behind the device of specialized MAC algorithms for wireless networks, and we will discuss in detail a specialized algorithm which is known as MACA. We will see the architecture of this algorithm, the functioning of this algorithm, and through the time state diagram we will see that what happens at sender and receiver and how these algorithms solve the problem of hidden and exposed terminal and near and far terminal problems. So the objectives of this module are: why medium access control is necessary in wireless environment, we will discuss. Then we will see that why there is a need of separate MAC protocols for wireless environment, what is hidden and exposed terminal problem, what is near and far terminal problem, and we will introduce an algorithm which is known as MACA algorithm, and we will see how it solves the hidden and exposed and near and far terminal problem. And we will also discuss the MAC protocols used by IEEE 82.11. What is medium access control? Medium access control is a protocol of data link layer. It is used to regulate the control of access of the medium among different users without or very less collisions. The transmission medium in wireless communication is air or atmosphere, which is shared by multiple users or subscribers. In such a situation, simultaneous access by multiple users may lead to collision. Hence, proper regulations for medium access control are necessary. Now, what is the motivation for specialized MAC in MAC environment? So, for this, let us consider an algorithm which is used in wired network, that is CSMA-CD. What is the abbreviation for this name? Carrier Sense Multiple Access with Collision Detection. Now, what is meant by carrier sense? That is, the algorithm senses the medium and then it transmits and then it detects the collisions. Let us, to understand this algorithm, let us first consider an analogy which we face in day-to-day life. That is, the analogy is a round table conference and the different people participate and communicate. They sense through their eyes and ears to find if anybody is talking. So if anyone senses someone talking, he remains quiet. That is, the sensing is listen before you talk. Now, this is how the medium is sensed. So, in real time also, when we want to transmit, we first sense the medium to be busy or free. So, if free, then the person talks, otherwise it waits. So, if no one is found to be talking, then the person speak. In roundtable conference, there is also a special mechanism applied in which there is a button which is provided in the front of the speaker. So when any person wants to speak, it presses the button. So when the button is pressed, the light on that button gets highlighted, and so the other people know that this person is speaking, so they will wait for their turn to come. Okay, so the users continuously listen to the medium to sense it is free, and if it is found to be free, then the person talks. Now, at time of talking, it also continues listen to the medium for any other collisions. So, and if it observes that the speech has coincided with some other person, it stops and then repeats its previous speech, because when it understands that the part of the speech has garbled up with some other speech, and therefore it again talks back. So what has happened in this analogy? The medium is sensed to be free or busy. It might be, the sensing might be through ears, through eyes, or as I said in a roundtable conference, by sensing the light of the button. If free, transmit, else wait. Then continuously listen to the medium for any collisions. And if the collisions are observed, stop and then repeat the previous speech. This is how the CSMA CD works. So it senses the medium. If free, it transmits, and then it continues to listen to the medium, and if any collision has been observed, stops the transmission, sends a jamming signal, and retransmits the packet. So this is how carriers sense multiple access with collision detection work. Now this scheme works very well in the wired communication. Why? Because all the devices are connected through the wire, and the strength of the signal is uniform throughout the wire. Hence all the device can listen to the medium and detect the collision if it exists. But this method of sensing and the collision detection might not work in the wireless or the mobile networks, because in wireless networks, the signal propagates in omnidirectional way in all the direction, and the strength of the signal decreases inversely as the square of distance from the transmitter. Also, the objects in the way from sender to receiver offers various effects like reflection, scattering, diffraction, leading to multipath propagation, and many other undesirable effects which degrades the signal. So the strength of the signal is not uniform throughout in wireless networks. Also, the receiving power is very much less than the transmitting power. Therefore, the wireless transceivers can't send and receive on the same time at the same channel, so they cannot detect the collisions. And most importantly, hidden and exposed terminal problem, near and far terminal problems fails the use of CSMA-CD in wireless networks. Now let us see that what are these problems and how CSMA-CD fails in the presence of these problems. Now what is a hidden and exposed terminal problem? To understand this problem, let us consider what are hidden terminals. As the strength of the signal transmitting from a wireless device decreases with distance, the transmission is limited to a certain area known as transmission range, after which the signal diminishes. We have discussed many times that depending on the power of the antenna, the strength of the signal will reach only up to a certain distance, and after that it won't be recognized. A device can listen only to those devices which are in its range, obviously, and hence others are said to be hidden from it. That means a device will sense only that device which is in its transmission range, and all the other devices whose transmission do not reach that device are said to be hidden from it. You can refer to the diagram. There are three devices, A, B and C. A is in the transmission range of B, that is the transmission of A can reach B and vice versa. B is in transmission range of C, that is the transmission of B can reach to C and vice versa. But the problem here is that you can see from the diagram also that A and C are not in transmission range of each other. They are said to be hidden from each other. So what is the scene of hidden terminals? There are three terminals A, B and C. A is in transmission range of B is in transmission range of C. But A and C are not in transmission range of each other. They are said to be hidden from each other. So what will happen in such a scenario when both A and C are wishing to transmit a packet to B? You can refer to the diagram. A wish to transmit. So it is applying a CSMA CD. For that, it senses the medium, finds it to be ideal. So sensing the medium to be ideal, it transmits. Now here C cannot hear the transmission of A. C does not know that A has transmitted. Why? Because the transmission of A does not reach C. A and C are hidden from each other. No problem. But the problem occurs when C also wish to transmit and it also senses the medium to be idle. Why? Because it is not sensing the transmission of A. So it will in no way understand that A is transmitted, and when it will sense the medium, it will find to be free. So here carrier sense fails. Now sensing the medium to be idle, it will also transmit and a collision will occur at B, because both A and C sensing the medium to be free are transmitting, causing the collision to occur at B. And the worst thing, these collisions are also not heard by A and C. Collision detection fails. Both continue transmitting because A and C are hidden from each other. Now these collided packets have to be resent, hence the hidden terminal problem drastically reduces the throughput. Now the other scene is also same, but it is posing some other problem. Now what is it? A and B are in transmission range of each other, B and C are in transmission range of each other, C and D are in transmission range of each other. But the thing is that B is transmitting to A and C wish to transmit to D. Now these are both are the different things. It is possible they can transmit without collision, but what will happen here? B is transmitting to A. Now this transmission will be heard by C. Why? Because C is in transmission range of B. Now when C wish to transmit to D, it will sense the medium to be busy. Now the thing is that the medium is not busy. B is transmitting to A, which is sensed by C as ideal, and when it wants to transmit to D, it is unnecessarily finding the medium to be busy and it is waiting for it to be free. It is refrained from transmitting. So this is the situation where unnecessarily C is waiting and the delay is caused. This problem is known as exposed terminal problem. So due to these two problems, we have seen that CSMA CD has failed. Another problem which occurs in wireless communications is near-far terminal problem. The problem is more acute when CDMA is used. Here you can refer to the diagram. A, B and C are three terminals in such a way that A is farther from A but nearer to C. That means the distance between A and C is more than the distance between B and C. Now if A and B both transmit with same power, what will happen that B is close to C, so there will be no effect on the quality of that signal. But since A is far from B, now when the signal from A after traveling the distance reaching C, the quality of the signal will be degraded. And in the worst condition, the signal of B will overpower the signal of A, it will drown the signal of A. This is known as near-far terminal problem and is more problematic in CDMA. So these are the two problems which exist with wireless communications. So to deal with hidden and exposed terminal problem, a special algorithm was proposed by Khan in 1990 to overcome these limitations. So in this algorithm, special control packets are used known as RTS and CTS. Before understanding the framework and functioning of this algorithm, again I would like to take an analogy in a real-time situation, and that analogy can be the solution to the hidden and exposed terminal problem, and that is what MACA algorithm uses. Now what is the problem here is that I take an analogy when three people are sitting and of which two people want to talk to the third person. Now these two persons are out of range of each other. They cannot hear each other. So when one person is talking, other cannot sense. It finds the way to be free. He also starts talking and both the conversation coincides at the third person. So what should be done? So the obvious solution is that before speaking, you ask to the third person that, are you free? Can I talk to you? And if and only if he allows, and then you start talking, because that third person can hear both one person's transmission as well as other person's transmission. So he can say very politely that no, I am busy. So you start your transmission only when I am free. This is a simple logic which is used in MACA algorithm. So this management of asking and giving the consent to talk is handled by two control packets which are known as RTS and CTS. RTS abbreviates for request to send and CTS abbreviates for control to send. As the name itself indicates, and as what we have seen in analogy, that RTS should be sent when any transmission is required and CTS would be sent as a consent to initiate the transmission. So RTS is a control packet used by sender to seek permission from the receiver to transmit. CTS is a control packet used by the receiver to grant permission to the sender to transmit. Now what information do this RTS and CTS hold and how these can be used to solve the problem of hidden and exposed terminals? RTS and CTS both contains the name of sender, receiver and the duration of transmission. We'll see that how these three information helps to reduce the collisions or to reduce the unnecessary weight as in exposed terminal problem. Whenever any station wants to transmit, it sends an RTS to the receiver. If the receiver is free, it signals the transmission by sending a CTS. The sender sends the packet, receiver receives the packet, sends the acknowledgement. Okay. Now we'll see that how with the help of this RTS CTS hidden terminal problem is solved. Again refer to this diagram. And the scene is A wants to transmit to B. It broadcast RTS to B. I am laying emphasis on broadcast. Broadcast means that when a device broadcasts something, all the devices which are in its range hears that particular transmission, while this is a broadcast medium. So A broadcasts RTS to B. This RTS is heard by B but not by C. A and C are hidden from each other. So RTS contains the name of sender, that is the name of A as the sender, name of B as the receiver and the duration for which the packet would be sent. But here what happens is that now B sends a CTS. It is free, so it sends a CTS which is heard by C. Why? Because B and C are in range of each other. Now on hearing this CTS, C finds that A wishes to communicate to B and it also finds the duration for which this transmission will take place. So it refrains itself for that duration to transmit. So C is not allowed to transmit anything for the duration mentioned in the RTS. So again, when C wants to transmit, it will send an RTS. If B is free, it will send the CTS, and then and only then C can transmit. So hidden terminal problem is solved. So before transmitting, both the devices are taking the consent of the receiver, and the receiver, if free only, it allows them to transmit. Hence, no collisions are there. Now, how exposed terminal problem is solved using RTS and CTS. What was the problem? B was transmitting to A. C wishes to transmit to B, but it unnecessarily waits because it hears the medium to be busy. Now here, when B wants to transmit to A, it sends RTS to A. This RTS is heard by C. A sends CTS. CTS is not heard by C, but it has heard the RTS. Now C understands that it is out of range with A, and looking at the RTS, it also understands that now B and A wish to communicate with each other, and if I perform the transmission with D, there will be no collision. So it sends RTS to D, and on receiving CTS from D, it starts transmitting. Exposed terminal problem is solved. So C does not have to wait unnecessarily for the transmission of B to stop. So we have seen that how RTS and CTS used in MACA algorithm solves the hidden and exposed terminal problem. But the limitations of MACA algorithm was that, firstly, it was just a three-way handshake. That is, RTS is sent, CTS is sent, data is sent. MACA did not provide specifications about the parameters, what are RTS, CTS, packet sizes, how to decide timers, and so on. Also, there can be collisions of RTS, that is, both A and C wish to transmit to B at the same time. Both of them sends the RTS, and there will be a collision of RTS at B. Now one can argue that the RTS and the CTS are control packets, their sizes are very small. So the RTS and CTS can be resent again. But this is affordable when the data packet size is large. So in that large, the overhead associated with the retransmission of that data packet is very much high as compared with the retransmission of RTS and CTS. But what if the packet size itself is small? In such a case, then the retransmission of RTS will be an overhead. So another, just a revision of MACA algorithm was proposed, known as MACAW. It is a refined and extended form of MACA. So as compared to MACA, it offers a four-way handshake. That is, RTS is sent, CTS sent, data sent, and the acknowledgement for the data is also sent. So sender sends, this is how four-way handshake of MACAW works. Sender sends RTS, receiver responds with clear to send, that is CTS. Sender sends data packet, receiver acknowledges with acknowledgement. RTS and CTS announce the duration of transfer. Nodes overhearing RTS and CTS keep quiet for that duration. Sender will retransmit RTS if no acknowledgement is received. So if acknowledgement is sent out but the acknowledgement is not received by the sender, after receiving new RTS, receiver will returns only the acknowledgement instead of CTS for new RTS. So let us look at the time state diagram for the sender and receiver for this protocol. Now what is a time state diagram? Time state diagram is a diagram in which the entity can be in different states of functioning, and then there are arrows or the links which are shown which tells that what event has triggered the transition from one state to another state. So we will understand the time state diagrams both for the sender and the receiver. Now there are three states in which the sender can be. In idle state, wait for CTS and wait for acknowledgement state. So when will sender move from idle state to wait for CTS state? When it has sent a packet, it has sent the RTS and now it is waiting for CTS. Now if a timeout has occurred, again it will send the RTS and it will be in the same state. Now when it will go from wait for CTS to wait for acknowledgement states. When the sender has received the CTS, it has sent the data, now it will move in wait for acknowledgement state. Now again it can go back from wait for acknowledgement state to wait for CTS state. When it will happen? When a timeout has occurred, that means it has not gotten acknowledgement, a timeout for acknowledgement has occurred or a negative acknowledgement has occurred. So in this case it understands that the data packet has not reached and it has to retransmit the packet. So it again sends the RTS because the RTS is necessary before transmitting the data, and then it goes back to the wait for CTS state. Right? So the sender goes from wait for acknowledgement to wait for CTS state when a timeout has occurred or a negative acknowledgement has occurred and it needs to retransmit the data, it sends the RTS. Now the sender will go from wait for acknowledgement state to the idle state when the acknowledgement has received and the loop is concluded. Similarly, the receiver can also be in two states, the idle states and wait for data states. When it will be in wait for data state? When it has received an RTS, it has sent the CTS and now it is waiting for the data. And when it will go from wait for data state to the idle state, when the data has been received, it has sent the acknowledgement, or when the timeout for the data has occurred and or a negative acknowledgement has occurred and the data is asked. So again it will be in wait for data states. Okay. So through this time start diagram we have understand the four-way handshake between the sender and receiver in MACAW algorithm. There can also be a five-way handshake when a sender sends RTS, the receiver responds with clear to send, data is sent, then acknowledgement is sent and the receipt of acknowledgement is also been sent. So to summarize with, what we have learnt in this module, we have learnt that medium access control is very important in wireless devices. At the same time, we have also learned that the protocols which are used in wired network cannot be directly used in wireless networks because of the problems associated, which are known as hidden and exposed terminal problem, near and far terminal problem. We have seen that what these problems are and how they reduce the performance. Right? And then we have discussed an algorithm which is specially designed for wireless networks to solve the problem of hidden and exposed terminal problem. Now this technique uses special control packets known as RTS and CTS which are sent before the transmission takes place. We have understood the framework and architecture of this algorithm, and by the means of a time state diagram we have understood the four-way handshakes which takes place between the sender and receiver when the transmission takes place. And we have also concluded that this algorithm very neatly solves the problem of hidden and exposed terminals.